Hello, welcome to the Medical Device Plug and Play Interoperability Lab. I'm Dave Arney, and this is Jeff Lord. We're going to be showing you our demonstration of patient-controlled analgesia safety interlock system. First, we're going to show you the physical setup here, then we'll switch to a screen capture and we'll walk through the software. So what we have here is a bunch of medical devices and patient simulators that we need to feed information to the medical devices so that we see patient vital signs coming out of them. On this side, we have the Philips Intelligent Monitor. Here we have a simulated PCA infusion pump. It's a large volume pump programmed to act like here we have a side screen capnograph and another patient monitor from ID. So a network switch where all the devices are plugged together. And here in the middle we have our patient simulator card. So it has a head, which we need for the pickup for the side screen capnograph. These are the patient's lungs. They're moving up and down, and they move by a ventilator sort of out of the shot. There's a tank of carbon dioxide that feeds just a little bit of CO2 into the lung so that we can create a carbon dioxide waveform that's picked up by the monitor. And here we have some electronic patient simulators. So the flu patient simulator is hooked up to the Philips here. And then we have another simulator from PCA that's hooked up to the ID. We have two electronic patient simulators just because we have two patient monitors. So that's our physical setup, and then we'll switch to a screen capture where Jeff will walk you through the software.
Here we see an app designed to monitor a patient receiving patient-controlled analgesia. In this case, the application is monitoring the data fabric for data that's been configured as relevant to this monitoring case. So you can see it's monitoring all sources of O2 saturation, respiratory rate, and end tidal CO2. In this case, we see a warning message indicating that none of the devices connected to the system right now are providing a source of respiratory rate that is required for the app. In our experimental setup, we have available a capnometry device which can be connected and supply respiratory rate. So Dave will demonstrate that now. So once the adapter is connected, a discovery process takes place within DDS, now advertising to the rest of the participants on the system data that's available, including respiratory rate and end tidal CO2 from that device. Dave is now showing us the small BeagleBone ARM-based computer that's running our software available on SourceForge. On the serial port side, it's speaking the proprietary protocol for each device. On the Ethernet side, it's utilizing currently RTI's implementation of DDS to create a global system data fabric that's then available to applications such as the infusion safety app that we're about to look at further. So you can see that the app has found sources of the data that it's interested in, including O2 saturation from both the Philips monitor as well as this IV monitor, and respiratory rate from an Iridian capnometer, as well as end tidal CO2 values from that same capnometer. So by virtue of DDS, this data could be coming from any device that was configured with the same data schema at the time that it was put together. So that information is all available on our SourceForge site to create devices that would interact with this app. So the first feature of this particular app that we would like to show is a transient desaturation event. Now, using the Fluke electronic simulator that's feeding optical signals into the finger clip connected to the Philips monitor, Dave is going to simulate a transient drop in O2 saturation. So this could be caused by a patient gripping a telephone handset, gripping the bed rail, or pretty much any movement can induce a failure mode of the pulse oximetry finger clip. So you can keep your eye on this dropping value from the Philips monitor. So now that we've dropped just slightly and temporarily, we see that the app generates a warning message And at this point, since the desaturation event has not lasted for very long, we don't generate an alarm, and the infusion continues. Now, if this desaturation event ends and O2 saturation climbs back up, you'll see that the message can clear and no nuisance alarm is generated in that scenario. So at this point, the patient's infusion of pain medication continues, and you can tell that somewhat from a green light on the pump over at this point in the picture. So now we're going to see what happens when two pieces of data, in this case when O2 saturation and respiratory rate provide a corroborating indication that the patient is deteriorating. So if they both move down simultaneously, we'll take action much quicker in that case, and you'll see that there will be a nurse call activated and the infusion will be stopped temporarily as an interlock until someone can come and intervene. So Dave is going to help us first to drop the patient's respiratory rate and also to create another desaturation event using the Fluke simulator connected to the Philips monitor. So the Fluke simulator generates optical signal that the Philips monitor can pick up. So we can already see, due to the reduced respiratory rate, end-tidal CO2 has picked up. The application has detected that, but it's only one factor. So now we'll see what happens as the desaturation continues. And there we can see that at this point, actually because of several factors simultaneously degrading, a drop in O2 saturation, drop in respiratory rate, and a rapid increase in end-tidal CO2 has caused us to activate a safety interlock, stop the pump. You can somewhat see that there is a extinguished green light on the pump to indicate that it's stopped. It's also indicated on the screen that the interlock has been activated, and a nurse has been alerted to come and check on this patient.